Welcome to the last video working through the solutions to the midterm review. This video is going to work through questions 31 to 38, which are the ones that are dealing with working with the special distributions that we've seen in Chapter 2. So the first one is talking about calls to a toll-free telephone hotline are made randomly and independently at an expected rate of 2 per minute. And we want to let x equal the number of calls received in the next 5 minutes. So first of all, anytime we're looking at something where we're looking at an interval of time or an interval of space and the number of events that are occurring in that time interval or time or space, we should start thinking about potentially using a Poisson distribution. The fact that we're told that the events occur randomly and independently and we're given an expected rate confirms that the Poisson would be the way to go here. So we know that the rate is 2 per minute. Our random variable is the number of calls in the next 5 minutes. So if I've got 2 per minute times 5 minutes, that's giving me 10. And that's going to be my lambda. So this is going to be a Poisson distribution with lambda equal to 10, which means that my probability mass function, little f of x, which gives me the probability that the random variable takes exactly the value little x, is going to be, remember, lambda to the x times e to the minus lambda over x factorial, with lambda equal to 10. That's 10 to the x times e to the minus 10 over x factorial. Now, to determine the probability that more than one call will be received in the next 5 minutes, that's the probability that the number of calls x is more than 1. The easiest way to find this probability, because we could theoretically have an infinitely large number of calls, is to use the complement and say, okay, well, this is going to be 1 minus the probability that x is less than or equal to 1, which is 1 minus f of 0 plus f of 1. So that's 1 minus 10 to the 0 times e to the minus 10 over 0 factorial plus 10 to the 1 times e to the minus 10 over 1 factorial. And if we go through and calculate this on the calculator, we come out to 0.9995. I'll just mention that if you were using a TI 83 or an 85, something that has the Poisson CDF, you could calculate this portion here using the Poisson CDF and putting in your lambda of 10 and your largest value that you're not to exceed, 1, and that will give you this piece here also. Okay, so moving on to the next scenario. Joe conducts telephone surveys for a large research company. For each shift, he's expected to complete a quota of at least 7 surveys. Normally, 1 in 8 calls that Joe makes results in a completed survey. We're going to let x equal the number of surveys completed after Joe has made 50 calls. So if we're assuming that the calls are independent of each other, then we've got a fixed number of calls that's going to be made, 50. We know that 1 in 8 result in success. And so since x is the number of successful surveys, x would have a binomial distribution with n equals 50 and p equals 1/8. And so what that means is that the probability mass function for x would be, remember, n 50, choose x, times p, 1/8, to the x power times 1 minus p, 7/8, to the 50 minus x power. So we want to know, what is the probability that Joe has met or exceeded his quota after making 50 calls? Notice that his quota is 7. So we're trying to find the probability that x is greater than or equal to 7, which, again, using the complement, is 1 minus the probability that x is less than or equal to 6. Right? Because if it's less than or not less than or equal to 6, then it must be greater than or equal to 7. So this is 1 minus the sum of x going from 0 to 6 of 50, choose x, 1/8 to the x power, 7/8 to the 50 minus x power. It's quite tedious to do all of this with the formula. If we were going to do it with the calculator, we can do this portion of it using the binomial CDF, putting in our n equals 50, our p equals 1/8, and the largest value that we're not to exceed here, 6. And we should come out to an answer which is 0.4363. And I'll just mention, if you do not have a calculator that does the binomial CDF, it would be very time consuming on a test for me to ask you a question that would require you to evaluate that 7 times. I won't do that, just so you know. If you are in a situation where you have to work with the formulas, I will keep it so that you only have to plug it in once or twice into the formula, so that you don't have your time sucked up by plugging things into the calculator. Okay, next scenario. We've got a public school randomly tests the hearing of students who have no previously detected hearing impairment. Among the children at the school, 15% have previously undetected hearing impairment. So we're going to let x equal the number of children screened until finding the first child with hearing impairment. Okay, so here, because we're randomly testing, we can assume that they're independent of each other. And we know that the chance that each individual person tested is going to have undetected hearing impairment is 15%. So I've got sort of independent trials with p equals 0.15. Now, I don't have a fixed number of trials, so this is not a binomial type situation. I don't know how many children are going to be screened, but I know that I'm going to try to think about screening until I find the first child with hearing impairment. The number of trials until the first success, we're going to consider detecting the hearing impairment as a success here, has a geometric distribution. So here, this is going to have a geometric distribution, and the parameter we need to know for geometric is p, so that's 0.15. When we want to find the probability that a child with hearing impairment will be discovered within the first 5 children, that would mean the number is less than or equal to 5 within the first 5. And we could find this a couple of different ways. Actually, I can think of 3 different ways. One would be to use the geometric probability mass function and evaluate it f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. That would be one possibility. Another would be to use the calculator. Say, okay, that would be equal to the geometric distribution CDF, putting in my p, and the value I'm less than or equal to, 5. So that'd be another way to do it. Or I could realize that if x is less than or equal to 5, what that means is that I don't have the first 5 results all be negative screenings, right? So not all of the first are negative. And if you think about the probability that all of the first 5 screenings are negative, the probability of each one being negative is 0.85. They're independent, so I can multiply the probabilities by each other. So all of those would give you the same answer, which is 0.5563. All right, and finally, our last 2 questions. We have a medical study, enrolls 200 volunteers, of which 45% are male. So just thinking about that, 45% of 200 is 90 male, and 55% are female, so 55% of 200 is 110 female. 50 of the volunteers are randomly selected to receive an experimental therapy. Now, since we're selecting people to receive a therapy, can tell this is going to have to be sampling without replacement. You wouldn't select the same person more than once to receive this therapy. So we're using n equals 50, and we're sampling without replacement. This is important because when we sample without replacement, the chance that the next person selected will be male depends on who was selected previously, right? And so we can't use a binomial distribution because we don't have independent trials, right? So right away we know without replacement can't use binomial, right? The remaining volunteers received standard therapy, and X is going to be the number of males who receive the experimental therapy, right? So here we're looking for the number of one type that are selected using sampling with replacement from a finite population. This is exactly the situation in which we use a hypergeometric distribution. With the hypergeometric, we have to specify a whole bunch of things. We specify the total size of the population that we're sampling from, 200 volunteers. We specify the number of the type we're interested in this case that's males, it's 90. We specify the number of the other type that we're not so interested in, females, 110. And we have to specify the size of the sample that we're sampling without replacement. There's 50. Okay. So now we want to find the probability that less than 25% of those receiving experimental therapy are male. So we know that 50 are receiving the therapy. 25% of 50 would be 12.5. So less than 25%, I can't have like values that are between 12 and 12.5 people, right? So if I have less than 25, what that means is I'm interested in the probability that X is less than or equal to 12. Now with the hypergeometric distribution, my probability mass function, remember, is N1, 90, choose X, times the number of ways I can choose from the 110 females, the other 50 minus X people, divided by the total number of ways I could have 200 people, of which I choose 50. Okay. So now to find the probability that X is less than or equal to 12, I'm going to take X going from 0 to 12, and I'm going to take this probability mass function evaluated each of those. 90, choose X. 110, choose 50 minus X. Over 200, choose 50. Evaluating this 13 times is super, super tedious, right? If you got this far, be happy. You didn't really need to plug all this into the calculator, but if you do, you should get an answer that comes out to be approximately 0.0004. So you have lots of tiny probabilities adding in there that all together come out to 0.0004. And again, I will not make you do something like this on the test. We have a very limited amount of time. There are 25 questions for which you have 90 minutes. So there's not going to be lots of intensive calculations. It'd be much more straightforward than that. Thank you. Have a good day.